Good morning to everybody. Welcome to the online workshop that we have organized dealing with the new scenario for high temperature performance materials and components. This workshop is going to be performed from 10 a.m. until 12 a.m. and we will discuss about aspects related to the development and the improvement of high temperature materials. The general picture that we want to transfer to you is that we can do that there are lots of things to do in the subject of high temperature materials, and under the project Hipermat we are developing different activities that are linked with these materials and different technologies linked to them to improve their properties, and we will try to transmit it to you. Well, the webinar is divided in 4 presentations that will take more or less 20 minutes each one. After each presentation, you are free to ask any question by means of the tool. Zoom allows to do that. You've got the button in my case is in the middle of the toolbar, more or less, in the bottom part of your desktop. So you can ask during the presentation the answers, and we will try to answer at the end of each presentation. Each of the presenters will try to answer them. So we will start without further delay with the first presentation. I'm going to present myself. Well, my name is Fernando Santos. I work in Fundación AZTERLAN. We are a research and development center located in the north of Spain. I work here since 2010, and I am responsible of the project officer and senior researcher in the area of steel and superalloys. I accumulate more than 20 years of previous experience as technical and quality manager in different metal industry companies. And I'm going to be the moderator. I'm the coordinator of the project Hipermat. I'm going to be the moderator of this webinar, and I'm going to make the first presentation. Well, we are going to discuss about refractory stainless steel chemical composition tanning for high temperature properties improvement. You know that these steels are mainly used in high temperature performance activities. I mean, they stand from furnace construction to application in turbines for high temperature applications. And nowadays, we think that there is a lot of ways or field of improvement. And in this case, talking about bulk raw material, bulk metallic alloys, I think that we will start with this presentation. Well, it's divided in 4 chapters. The first one is the introduction. We are going to discuss about failure mode analysis of components and materials. Then we will make an overall approach and methodology for the formulation of new refractory stainless steel alloy grades. And in the end, we will have an idea of the final conclusions. Well, a small introduction of our research and development center. We are strongly industrial oriented. We work with a lot of industrial companies, not only in a region, but outside also. We have quite a good range of equipment and facilities. We are members of the Basque Research and Technology Alliance, BRTA, and we work in European and world level networks. We have different European projects. We belong to the Basque Science and Technology Network and to the Spanish Technology Centers Network. And our main fields of action, we are focused on developing new materials, in improving and developing solutions for manufacturing processes. We develop artificial intelligence and advanced technological solutions for the industry, for the metal industry. And we work on sustainability and energy and other related areas like environmental issues and anything that the metal industry that is around us needs. Well, which is the current presentation, as I have explained you, is supported in the studies and developments that are being carried out within the Hipermat project, financed in the framework of Horizon 2020 program. Well, the objective of this presentation is to describe the methodology that is being used for the development of robust and sustainable solutions in terms of new steel alloy grades for high temperature applications. In the right, you can take a look at the current design scheme of different grades of stainless steels. Let's say that the general picture that we can see is incomplete as far as decision making of how to modify chemical compositions to arrive to a success alloy is quite more complex than that. We are trying to explain in next slides the methodology and tools that we use for a successful new alloy grades generation. I think it's not so easy as to decide that I add these chemical compositions, I obtain that. There are much more aspects involved in this design. If we go ahead, we have quite clear that the basis for formulating a good solution is to making a previous very good analysis of the situation. So it's very important to make a failure mode analysis of components and materials. It's critical to define corrective actions so that based on that, to assure the accurate selection and development of the different alloy grades. Well, failure modes, we have two main aspects. We have failure modes that can be divided in two big groups depending on the origin of the root cause. For example, those due to a root cause link with the manufacturing process of the component, mainly linked with the bad chemical composition, cracks on surface, for example, zinc grades inclusions, defects generated during the process manufacturing. And those linked with the microstructure degradation due to the manufacturing routine or the furnace environment. As you know, if you come from the industry, the failure mode effect analysis is at the starting point, taking into account that only the failure modes with the most significant severity of the effect, the higher level of occurrence and lower detection possibility are taken into account currently in these components. Let's say that, let's put some examples. In the case of severity, for example, one failure modes that take place in the long time or doesn't represent productivity or energy losses should be replaced by other failure modes that perhaps has lower occurrence but being catastrophic in terms, for example, of security of the worker, productivity, or energy consumption. Let's put another example of what a bad analysis of the failure mode. For example, if we identify a problem as creep, and it's not creep, it's thermal fatigue, the final solutions that we will give in terms of chemical composition variation is going to be very different in one case or in the other. And what is more severe, we can decide on taking one decision related to chemical composition that it's going to affect adversely to the final performance of the part. So as I have said, it's very important to define very well the failure mode and also the root cause. We will go further on this in next slides. Okay. Here we have the scheme. How do we define this failure mode? First, we have to analyze the type of failure with the highest risk priority number. Then from then on, we divide in two main root cause types. Those that are linked with the chemical composition and furnace working routine, and those root causes link with the component manufacturing process and furnace working routine. In the case of the defect, the root cause is linked with the chemical composition, we should define changes in chemical composition generating new alloy grades. Whereas in the other case, we would have just to adjust the process performance or change the process or make modifications in the process to avoid this failure mode to take place. So this is the line that we will follow in our case, because we want to define, we understand that the components that we are using are under control. And we are going to select the other way, the way that we have to improve their quality, the performance of the material, to avoid stops of the furnace and to improve the behavior of the furnace. For example, this is a brief example of how we identify the failure mode. Let's situate ourselves in the furnace that is working with loads and over components, and they are suffering continuous loads to high temperature. This generates creep. How we identify creep? Well, creep normally we identify it by means of micrography. If we observe quite clearly that there are cracks parallel to the fracture surface and propagating through the interdendritic spaces, is clearly creep. So this is an example. You can see the metallography. You can see the cracks, and they are moving through interdendritic spaces. What about thermal fatigue? Well, thermal fatigue has like beaches. It's like smooth beaches that have been progressing, moved by the different cooling and heating cycles. And you can see on the right how they have been moving and how there are smooth surfaces that can be observed quite clearly by loop, not necessarily by microscopy many times. So if I have explained before, if we misunderstood the reason, the root cause, sorry, the failure mode, we can take actions that won't be adequate for solving the problem. Okay. What's wear? We can have problems with wear. Well, we will analyze, we will detect a dimension reduction from the original value, and we will show a surface that in our case is decarburized, has lost the presence of carbides, and it's more prone to wear. And of course, the formation, we can observe in the right image that we have a flatness variation in this control surface. So this is some examples of how to define the failure modes in a correct way, so that we can define robust corrective actions. Well, which is the methodology for the formulation of the new refractory stainless steel alloy grades? Well, here we don't have to lose the reference that we have been discussing before. The methodology includes the preliminary failure mode and root cause analysis, and continues with the definition of actions for the formulation of the new refractory stainless steel alloy grades. Here we see, for example, a reference alloy that we are using. It's been used in many high temperature applications. We have to base our decisions first on bibliography. We have to analyze, by one side, made a table with the main chemical elements affecting material properties, and by all the other side, main phases that can appear and the relationship with material properties. And we have to link both of them. We will see an example later. Once this has been finished, chemical decision, the decision of changing one chemical element, has a significant effect, can have a significant effect on process performance. So we need an expert knowledge that decides based on the analysis that has been made, decides on adjust current chemical composition ranges or reference alloys, or introduce new chemical elements. This is critical, and evaluate the effect of process performance. I think that you know that many chemical composition ranges are needed. It depends on the process that you can make them wider or narrower. So you must know about the process, and you have to be conscious also that perhaps some chemical elements that you introduce cannot be introduced so easily, and you need additional process modifications to introduce them. So not only the decision over chemical composition is important, but the expert knowledge on process is critical for a successful integration of these chemical elements into the alloy grade. Once we have finished with that, we can go ahead with the modeling for process performance and material properties prediction. We can go directly to the process with these materials. We have to check whether the properties of these materials are going to interfere with phase. We have to check that what has been observed in bibliography is really observed by modeling, and they don't interfere in the process itself, in the filling, for example, and solidification, in the cooling. We have to check that. And then once we have this general picture and we have go over a robust design of the alloy, we can go on the we can transfer that to the real process, to the final process. Okay, if we go ahead, this is an example. For example, first we have a table with different chemical elements and the effect on mainly on properties. Let's put the example of niobium. We chase niobium, it has a hardening effect. It's positive for us. We need hardening to withstand high wear, higher mechanical properties to support higher mechanical loads. So this will be our first picture of the chemical elements and their effect on different properties. And we take this picture, and next to that, we make also an analysis of main phases that appears and the effects of this element that this element can have in promoting or not this type of phases. And you can see highlighted in yellow that niobium has a positive effect on hardening, but at the same time is promoting the generation of different phases. And some of them are not good phases. They are detrimental for the final properties. So we have to take a lot of care about that. Changing one element can promote changes and generate different phases that are going to be generated or not, depending on the process characteristics and on the furnace routine also. This will be the first stage. Once we have all this information of phases and chemical elements, well, we have to make the adjustment, we have been discussing that, of the current chemical composition ranges of reference alloy under a technical and economical feasibility point of view. We have to check the capability of the process to support tighter composition ranges of the alloy, together, for example, with the estimated price increase of the alloy in case higher value-added chemical elements have to be maintained in the top range of the specification, or by the addition of new, very high value-added chemical elements. Of course, the introduction of new chemical elements in the alloy grades formulation has to be compatible with the manufacturing process. For example, introduction of highly reactive elements with oxygen, such as titanium and aluminium, require the manufacturing of the alloy under vacuum or special process conditions. In the same way, the estimation of the long-term benefit of the alloy, reduction of the stock and consumption of spare parts, has to be compared with the cost increase of the required element or the additional characteristics, if any, of the process performance. So we don't have to never forget about the process, because the process is going to be critical and determinant in the use of different alloy grades. Well, next to that, following to that, in the sim that we have seen before, we had said that modeling is very important, and we will explain why. Well, we can take a look to the right, and we can take a look at the phases generation. For example, we are representing the phases generation, the liquid, how the liquid is transforming into different phases, and at which time, at which temperature are being generated. And we have in dashed lines, it will be the variation when they appear or not, depending on different ranges of the chemical composition of the alloy. So we can see that it helps us to manage very well the effect of this chemical composition on solidification ranges, on appearing of different phases. It's quite critical. Let's say that, for example, this thermodynamic study, and the process point of view, these parameters are critical as far as they are determine the trend of a cast alloy to shrinkage, for example, to hot-tearing, to solidification, and weldability. It's very important to take that in consideration. What this modeling also allows us to do, the modeling, the solidification that we have seen before was in equilibrium, but normally this never happens. The cooling rate is higher than that a very slow cooling until equilibrium is achieved. There are other models that are used to fix last solidifying temperatures of the different alloys phases when segregation occurs and no back diffusion is considered. The analysis of the two diagrams based on type of phases that will be present and the temperature when they appear will be the basis for an estimation of the mechanical properties and, well, in next steps, not only mechanical properties, also corrosion properties in next steps. Well, why is so critical the information that modeling is giving us? Well, it defined quite clearly the required heat treatments in post-processing steps to assure one cycle to remove or prompt or promote the precipitation of phases. We are going to use that to fix the heat treatment temperature. Depending on these ranges of chemical composition are going to give us when these phases are going to precipitate, and we can assure the temperature of heat treatment. Well, we can also analyze the cooling rate during process performance. We can decide if we want to demol more quickly or not, depending on the phases that we want to maintain in the final structure. And of course, we can determine the evolution of the microstructure from the metastable condition generated by the solidification range of the previous heat treatment during the working performance of the furnace. For example, we have to consider that the microstructure is not can be modified at high temperature during the performance of the furnace, and this modeling can give us a lot of information about how it will evolve with the time. Okay, so conclusions. So it's what can we are now ongoing with the development of new alloys. The evolution of these alloys, we have preliminary data of tests of CRIP. It's quite promising, the selection of chemical composition and additions that we have made. We are obtaining at this time improvements of around 10 and 20% of CRIP. We have to fix that and to consolidate, but of course, preliminary data are quite promising. But in general, let's say that the strategy for new alloys development requires a first in-depth analysis of the failure mode to act accordingly over the real root cause. The first approach for an adequate chemical composition selection is the bibliographic analysis of presence and the effect of different phases on alloying properties, followed by the effect on phases generation and on hardening mechanisms of the different chemical elements. Once most adequate chemical elements are identified, technical and economical feasibility has to be prepared by means of expert knowledge to fix the composition ranges and the process flow chart. And finally, the use of modeling softwares can validate the previously defined proposed chemical compositions and preliminary analysis, assuring a more precise approach to the final solution. And this is basically everything. So this is me, Fernando Santos. If you have any doubt, of course, you can ask me, and open to any question and to any doubt that you may have. Okay. So. Okay, there is no question. Well, I will just introduce next speaker. Next speaker will be Surbi Sivaji Jogda from KTH, Royal Institute of Technology, Sweden. Yes, okay. Surbi has a master's degree in engineering material science and currently pursuing her PhD degree at the KTH Royal Institute of Technology, Sweden. Before coming to Sweden, he has completed her bachelor degree in metallurgical engineering from College of Engineering, Pune, India. She will start with the next presentation. Following, it will be complemented. It will be followed by it will be divided in two speakers. The first will be Surbi. The second one will be David Linder, that has a master in material and nanophysics from Linköping University in 2015 and a PhD in applied materials science from the KTH Royal Institute of Technology in 2020, and currently is working as a material design engineering at QUESTEK Europe since 2019. So he will continue with the second part of the presentation. So, Surbi, are you there?
Yes.
Perfect. We hear you perfectly. So, if you want to go ahead.
Sure. Thank you, Fernando. Yeah.
Thank you.
Good morning, one and all present here. Myself, Surbi Sivaji Jogda from KTH Royal Technology, Sweden. Today, Dr. David Linder from QUESTEK and I will present about the topic high entropy alloys and superalloys existing alternatives for high temperature applications. To begin with, the goal of Hypermat is to achieve improved lifetime of rings and beams of rolling beam furnace used for hard stamping. Here we can view the photo of hot stamping process. There are two main paths focused in this project. First, the entrance of the furnace, where it undergoes fluctuating temperatures ranging from 450 degrees Celsius to 750 degrees Celsius and under high loads. And the second part of the project is focused on the inside the furnace, which experiences corrosive environment and continuous high temperature ranging temperature from 930 to 970 degrees Celsius. These working condition leads to failure modes of thermal fatigue, corrosion, creep, and wear, which were explained in details by Fernando in the last presentation. So the aim of this project is to achieve the performance for these beams and rings, and the performance requirements includes yield strength and thermal stability at 930 degrees Celsius, and creep resistance and wear resistance at service temperature, along with thermal fatigue resistance and oxidation resistance at elevated temperatures. Next, we move on to the existing potential materials for high temperature applications. First, let us begin with high entropy alloys. The initial research period for high entropy alloy was mainly focused on 3D transition metals from the period 4 of the periodic table, period 4. However, these high entropy alloys failed to operate above 600 degrees Celsius. Further, the secondary research period included the refractory high entropy alloys. In 2010, the first refractory high entropy alloy was developed using 5 refractory elements of molybdenum, niobium, tantalum, vanadium, and tungsten, which showed superior high temperature mechanical properties, mainly above 1000 degrees Celsius. Subsequently, many researchers have incorporated refractory elements from group 4, group 5, and group 6 from the periodic table, highlighted in sky blue here in the periodic table, which has enhanced the mechanical properties at wide temperature ranges. Here on right, we can see a periodic table highlighting different colors with the most typical high entropy alloy families. Some more details about refractory high entropy alloys. These are promising materials for high temperature applications due to its high melting and outstanding temperature strength, as well as high mechanical properties at different temperature ranges. Refractory high entropy alloys are also thus considered as a future alloys and to replace the current nickel-based superalloys for high temperature applications. Now, if we consider this graph on right side, we have yield stress versus temperature graph, and the hollow geometry refers to the refractory high entropy alloy, and the dash lines represents the nickel-based superalloys. Here we can see the encircled refractory high entropy alloy, and its derivatives mostly retain superior mechanical properties up to 1000 to 1200 degrees Celsius, whereas refractory high entropy alloys with presence of tantalum and tungsten also maintains interesting properties at high temperature applications. It is very interesting to note that the nickel-based alloys drop their strength over the range of 700 to 900 degrees Celsius, whereas refractory high entropy shows exceptionally good properties at high temperature. This was all about the high entropy alloys. Now we can consider superalloys. And superalloys are mainly classified into three types. That is nickel-based, cobalt-based, and titanium-aluminium-based superalloys. And precipitation, solid solution strengthening, and dispersion strengthening are the main strengthening mechanism used for superalloys. And they show unique capabilities of maintaining a high yield strength, tensile strength, creep resistance, corrosion resistance, and fatigue resistance at elevated temperature. It is great to note that outstanding creep and stress rupture resistance of nickel superalloys at high temperatures make them very promising, whereas cobalt-based superalloys are not as strong as nickel-based superalloys, but they retain their strength up to high temperatures. Inconel, VASPA alloy, rain alloys, Haynes alloy are few of the very well-known examples of superalloys. Moving further on, here is a map of some of the most commonly used nickel-based superalloys for high-temperature service. And in this map, we can see the plus signs denotes the addition of the elements, whereas the minus sign refers to the removal of the elements. And as we can see, the different strengthening mechanism and effect of alloying elements on the final properties of the superalloy. For example, if we consider alloy 600, on addition of chromium, molybdenum, and niobium, we achieve alloy 625 with improved corrosion and improved strength, and so on. Now some comparison of refractory high entropy alloy and superalloy. On the left side, we can see a graph for yield strength versus temperature. And the solid geometries here refers to the refractory high entropy alloys, whereas hollow geometry refers to the Inconel and Haynes 230 superalloys. So if we consider the graph here, we can see the yield strength of the green and purple refractory high entropy alloys have virtually remained same, unchanged over the range of 600 to 800 degrees Celsius, whereas the superalloys drop their strength over this temperature range. Also, it is interesting to note that the two alloys have extremely high yield strength for over 400 MPa at 1600 degrees Celsius. Also, the tungsten containing refractory high entropy alloys have excellent resistance to thermal softening. here there is a comparison for simpler refractory alloys on left side graph, whereas yield strength versus temperature for refractory high entropy alloys on the right side. It is interesting to note that above 1000 degrees Celsius, the simple refractory alloys drop their strength, whereas the high entropy alloys maintain their strength above 1000 degrees Celsius for above the 400 MPa, even at 1600 degrees Celsius. And there is exceptional for simple refractory alloy T111, which is used in aerospace, and they show exceptionally high yields, exceptionally good properties at high temperatures above 19-20 degrees Celsius. This was all about the high entropy alloy and superalloys. Here is the assessment of benchmark materials and modification strategies for Hypermat. The refractory high entropy alloys can be considered as promising materials for high temperature applications because of their outstanding high temperature properties. Addition of niobium, molybdenum, and tantalum can maintain high strength even at 1200 degrees Celsius, which is superior to traditional superalloys such as Inconel and Haynes 230. Also, modification strategies can include tungsten addition, which can show excellent resistance to thermal softening. Whereas, on the other hand, the superalloys show exceptionally outstanding properties over the range of 600 to 800 degrees Celsius, and can show better properties with some modifications. Apart from this, it is very essential to consider the cost efficiency, and high entropy alloys tend to be very costly in respect to superalloys. And therefore, for Hypermat, the high entropy alloys and superalloys are considered as a coating, as a laser melt deposition coatings than the bulk material. Based on the literature survey, Hypermat preliminary material selection has resulted in 3 alloy suggestions for LMD. First is nickel-based superalloys, the alloy 230, which has plus points of strength, microstructural stability, and absence of aluminum can enhance the oxidation resistance, and it is also available in the powder form to further develop the superalloy. And the disadvantage of this can be the high tungsten content, which can make it difficult to achieve crack-free coating layers, and also due to WC carbide formation, there can be embrittlement at the coating layers. So the backup of this superalloy could be alloy 625, in which there is absence of tungsten. Second is transition metal high entropy alloy. And this has been selected on basis of their high oxidation resistance, and they tend to form less carbides, and also has relatively low elemental cost. It is also important to consider the technical as well as business risk in this. So it can, the lack of commercial powders can be a drawback for developing such high entropy alloys. Therefore, in this case, if there is insufficient strength or wear resistance for the selected high entropy alloy, there is the backup selected is addition of copper. And the last one is refractory metal high entropy alloy. And overall, this one has many drawbacks than advantages, but we are focusing more on its ICME tool and modeling to achieve the development of refractory metal high entropy alloy. Now I would like to invite David for explaining more about modeling and ICME tools. Thank you.
Yes, thank you, Surbi. I think this is a nice overview of potential alternatives. So I'll be trying to step through a bit similar to what Fernando was talking about. One of the approaches that we're using in the project and how to evaluate these different materials. And as mentioned before, the current materials that is being used is an austenitic stainless steel. It's conventionally cast. It has a rather conventional specification, and it has advantages and drawbacks as any other material. But looking into the Hipermat project, as Fernando was talking about, the updated or modified specification of the stainless steel is one of the things we're looking into. But also, as Surbi mentioned, LMD coatings applied onto the steels of either nickel-based superalloys or high-entropy alloys to improve the performance. But adding new processes, combining an LMD coating on top of a cast steel adds a lot of added complexity, and furthermore, combining different materials also adds a lot of complexity. So the current focus has been on understanding and modeling the different process structure property relationships that we see within these materials. And on the left, you have the three-link chain relating processing structure properties, and properties performance. And there are a lot of different linkages that one could evaluate and model in these materials, but to really emphasize and focus on the right things, as Fernando was talking about, the root cause or finding the key performance drivers or performance driving properties is one of the aspects that has been ongoing work in this project. And since the failure mechanisms vary quite a lot, depending on what part of the furnace and what component specifically we're looking at, achieving the performance goal of enhanced furnace component lifetime is not straightforward, and will likely require different solutions for the different components. And this would, of course, entail a different type of property trade-off. Here on the right side, you see examples of different properties that could be influencing or driving the performance depending on the location in the furnace. So really finding an optimal property trade-off for the different components, either with updated steel compositions or with new LMD coatings on top of this, is key. But not only performance. I think we jumped one too far now at this point, Surbi. Yes. That's one end of the chain, really translating performance into property targets. Whereas then the other end is identifying potential processing routes and maybe even more critical, identifying processing constraints. And this is an example of some type of bulk steel going through the entire process from refining and deoxidization through casting to different heat treatments. But then with adding on top of it an LMD coating, we're adding a lot of different steps. And all of this could lead to different bottlenecks in the development, and is really related to the LMD coating with the optimization or the processing of the LMD coating that is putting a lot of constraints on the use of the refractory high-entropy alloys in this project, since there are a lot of unknowns. So the focus currently is more towards the steels, the superalloys, and the transition metal high-entropy alloys, with some aluminum additions for potentially added strength from precipitates. Examples of how one could move along modeling these things is the same plot as shown by Fernando. Just want to show that how one can use it to understand the influence of composition on phase formation in the benchmark material or in the standard material here. And as Fernando already mentioned, full lines is for one composition within the specification, and the dashed and dotted lines are for other compositions. And specifically, this is focused on carbon content, where you can see the red lines for low carbon content. It's the dotted line where the sigma phase forms at around 900 Celsius, whereas for the high carbon content is the dashed line where the sigma phase formation temperature is significantly lower. And this could be has been help understanding the base material failure modes where sigma phase formation occurs at the decarburized surface layer, etc. But also similar calculations have been performed for investigating the effect of different alloy modifications on the base steel phase fractions. So I think we can move on to the next part. So that's only looking into the casting of the steel, but if we look into the more complex process of adding an LMD layer on top of this, and then potentially heat treating it otherwise, and then seeing the effect on the final performance, we outline a systems chart highlighting the process structure and property relations, and I've been working on identifying different microstructural features that could be expected to be critical for the actual properties and the performance. So all of these are, it's quite complex, with the substrate that behaves in a certain way, we have the coating that behaves in its own way, and then we have the interface where we might be seeing formation of different carbides or intermetallics, etc., during the coating process, but also in service. So the next steps that we're working towards is to quantify these key linkages by modeling, process simulations, and selected experimental studies moving along the project. And here is an example of how we are combining material modeling and process simulations that are performed at ESI by generating material parameters for simulations for the LMD process, for example, also the hydrosolidification process. The example here is for specific heat as a function of temperature, where we can see that using modeling, we can extend upon the ranges available in literature or in data sheets, and enable more reliable simulations of this new process. And feeding this into the ESI simulations, we can then get, for example, melt pool size or time temperature profiles as shown here. We can move to the last slide. And moving forward in the project, the idea is to really make this into or work with this combined framework for LMD process and alloy optimization, where the first steps we've shown on the previous slide was generating input parameters, but then utilizing these simulations for process simulations would allow for a more accurate description of the time temperature profile that is seen during the LMD deposition, which we can then plug into our other material models to work on predicting as-built microstructures and mechanical properties, which could then help further alloy optimization, etc. And this could then be a repetitive loop working on this. So that's an overview of how we are currently working within the project. Thank you.
Thank you very much, Ruby and David. Okay, so I see that there is no questions elsewhere. So I think that we can give the floor to the next presentation. Okay, next speakers are going to present a presentation link with LMD application. I'm going to introduce to they are going to share the same presentation. The first one is going to be Sergio Usejo, is the Director of Additive Manufacturing Cell of CEIT Research and Development Center. He has a Master in Mechanical Engineering and PhD from the University of Navarra. He currently works on process optimization for laser metal deposition, which is an additive manufacturing technology. And the second speaker is going to be Dr. Mustafa Megahed, works for AC Group as scientific director with focus on modeling manufacturing processes. He has a degree in mechanical engineering and has been working in the field of simulation-based engineering since 1993. So you've got the floor, Sergio. You can start with the presentation, please. Go ahead.
Just give me a second.
Oh yes, now yes, we can hear you.
Okay, I will share my camera. Okay. And just a second. Okay. So thank you. Thank you, Fernando, for your introduction. In this last presentation of today's webinar, my colleague Mustafa from ESI and myself from CEIT are going to present the LMD technology for coating in this project, the experimental data for simulation validation, and the simulation methods and results obtained so far. The LMD technology goes by many names. Some of them can be, you can see on the slide. For example, laser metal deposition, laser cladding, direct metal laser deposition, laser engineered net shaping or lens, direct light fabrications, laser directed energy deposition, and some others that are not here, but all of these names refer to the same technology. And in this presentation, we will use the LMD concept or name. So LMD is an additive manufacturing technology, or metal 3D printing, if you want, where the raw material are metallic powders, and the energy source to melt these metallic powders is a continuous laser. Let's start with the raw material. The metallic powder is produced by gas atomization, usually using an atomizer. This is what you can see on this figure. The molten metal that is here, this is an induction furnace, passes through a die, that is this part. And at this point, you can see here the die of a picture of the actual die. At this point, the gas flows at supersonic velocity here and meets the molten metal. And this molten metal is divided in small droplets that solidify during flight. The powder size used for LMD technology is usually between 20 to 45 microns or 45 to 100 microns. It's depending on the equipment you are using. Ideally, the powder should be spherical with low internal porosity. You can see on this picture that the porosity is very, very small, and no satellites. Satellites are these small spheres attached to the bigger ones, and the powder flows better with no satellites. So that's the reason to prefer no satellites. We are going to see a video, a very short video of the process. In blue, we can see the jets of powder that meet at a point, and there the laser melts the powder. The molten metal volume is usually called the melt pool or molten pool. And in this case, we see that the part being manufactured is rotating while the LMD nozzle is not moving. Okay, let's see now in more detail what's going on during the process. We see that the powder that is this dashed line, the powder meets at a point, and at this point, the laser in dark blue meets the powder, and a melt pool appears. There is also a shielding in light blue that protects the melt pool from oxidation. If the base plate of the base material is fixed and the nozzle, that is this part, is moving, we leave a track of deposited material. And if we look closely, we can see that in the base material is melted below the deposited material that is on top. Yes, in this code, it is called fusion zone. This melted material in the base material. So this means that the powder material will be mixed with some quantity of the base material, and this will affect the properties. There are many parameters that influence the LMD process, and we are going to see the main parameters. So the laser power is one of the key parameters. The more power, the more material is melted. The laser spot diameter is the size of the laser beam at the melt pool. Here, there's the melt pool plane. Yes, as you can see in the picture, the laser spot diameter can be smaller or bigger and can be changed by moving a lens in the optics. The other lens is usually fixed. Regarding the powder, the main parameters are the powder spot size, which is the minimum diameter at the powder cloud. You can see here, this is the powder spot size. The working distance is the distance from the end of the nozzle to the powder spot size. And it's important to adjust this working distance properly. The carrier gas flow rate is the liters per minute of the gas that carries the powder, which is usually argon. And the powder feed rate are the grams per minute of the powder that pass through the nozzle. We have also a shielding gas flow rate we have seen before to protect the melt pool from oxidation. And what we can see on these micrographs is that both the carrier gas and shielding gas have a quite big influence on the shape of the track. You can see here we have clad with a bigger height, and just by changing the carrier gas and shielding gas, we can reduce this height. The other parameter is the process velocity or scan speed. It is the speed at which the nozzle is moving if the base plate is fixed. And finally, we can use different building strategies. We can change the overlap, the horizontal overlap. We can see here on this picture. It's called lateral overlap or horizontal overlap. We can adjust the vertical overlap. And there are different strategies to produce a part or a coating. Yes, like this one, this is called one way, this is called zigzag, spiral. Okay, so for the validation of LMD simulations, we have done some experiments. Okay, the simulations tools are developed by ESI. That is the next part of the presentation. The base material we have used for this experiment is IC310, that is the furnace material. And we are going to test 3 powder materials, as Surbi has explained at the beginning. Haynes 230, which is a nickel-based alloy, and 2 high entropy alloys. Both are similar. The only difference is that one of them has copper and the other hasn't. We have built several single tracks in 2 different design of experiments. And we have characterized the main geometrical measurements using an optical microscope. For example, the height, width, clad area, the elution area, and the dilution of the percentage. The data exchange with our partner ESI are micrograph, main process parameters that you can see in this table, and the geometrical characterization. Now, in the next slide, Mustafa from ESI is going to present the work of on-process simulation. Mustafa?
Yes, just unmuting, and now I am there. Okay, thank you for the introduction. So the LMD process presented by Sergio, we attempt to model it in the same sequence as the process performs. So we first have to deliver the feedstock to the model, and that implies we have to resolve the nozzle, the delivery nozzle, and the flow fields inside these nozzles. So we represent the nozzle using a computational grid as shown on the right-hand side. The grid has different solid domains, nothing flows through there, and several, let's say, fluid domains. Those are the ones where we define the carrier gas flow, that is the gas that is carrying the powder to the delivery point, shield gas, which will shield the processed area from oxidants or other impurities. And we also represent the powder as discrete particles, and to identify how they how their trajectories look like after they come out of the nozzle. The models used are based on computational fluid dynamics, CFD, where we use an Eulerian representation for gas flow and a Lagrangian formulation for the particle tracking. So each particle or parcel of particles is tracked separately. We take the powder size distribution into account. So you will see that larger particles will have a larger mass and a higher inertia, so they will probably fly towards the point of intention, whereas lighter particles may be disturbed by cross-flow or switching of directions of the shield gas, so the smaller particles might be lost for the process. So the size distribution is an important factor to identify how much of the powder is really captured in the med pool. We account for the drag between the gas flows and the different particles. Here we take into account things like turbulent drag, particle sizes, and the concentration of the particles. And we also take collisions of the particles with different walls. This collision will extract energy from the particles, and the remaining energy will be the remaining kinetic energy for the particle to continue its trajectory as it moves out of the nozzle. The result of these simulations is the particle trajectories. We can extract the standoff distance or the working distance between nozzle and base plate, as shown on the right-hand side. For these flow conditions, we achieved a minimum focal diameter at about 20 millimeters away from the nozzle mouth. And we can also identify the focal size. As you see, because of the collisions of the particles with the walls, and also because of crossflow, some of the particles move sidewards or don't even move towards the focal point. Those particles are usually lost to the process. And if you count these particles, you can actually calculate an efficiency of powder capture. That is usually around 60%, which we did not quantify for this particular case here. The next slide, please. Okay, so now we have the feedstock delivery. We know how the particles are flying towards the point of deposition. We also have parameters, including laser power and the spot size. We have the scan speed, how fast the nozzle is moving on the substrate, and we have the material properties. We know that we are depositing, in this case, Haynes 230 on a steel. So the material properties of both substrate and the deposited material are known to the model. In this case, we are also using a computational fluid dynamics. In this case, it's a three-phase flow. We take into account the solid phase, and molten material will be solidified with time. We have the liquid. As the laser processes the material, it liquefies it. So we take into account liquid state. The liquid state has a lot of complications in the sense you have surface tension, and because of the dependency of the surface tension on temperature, you will have things like Marangoni playing a major role on how this would look like, how the deposition at the end looks like. And if the energy delivered is too high, so if you have a high power, you might even evaporate the metal. That has several implications on how the metal pool will look like. Evaporation plays a smaller role in LMD, but it still takes place and it is accounted for in radiation modeling is quite important for LMD. There are other additive processes where radiation can be simplified to a very simple, analytical formulation. But in LMD, you have to resolve radiation in a more elaborate manner because the nozzles used are usually coaxial, meaning the laser is delivered through a central hole of the nozzle and particles from the laser. So you have actually scattering of laser power actually reaches the substrate. So the amount of energy reaching the substrate or absorbed by the powder before it actually reaches the substrate are things which are calculated in the model and are extremely important to capture the med pool dimensions correctly. What we get out of this model are the med pool dimensions, local cooling rates, and the powder capture efficiency. So the capture efficiency here in this sense will include how wide is the med pool and how much of stray particles are still captured by the med pool. So the result of powder efficiency is not only a nozzle question, but it's also the combination of nozzle, standoff, and med pool size. On the right-hand side, an animation was running showing you the starting point, which is usually not the final state of the melt pool. We run the melt simulation until we get a quasi-steady deposited line. And at the end of that line, we extract the data we would like. Data would include things like melt pool width, height, and depth. Here in this case, Sergio furnished us with some very nice validation data. For one set of parameters, you see here a height of 0.85, which is in the simulation, it's predicting 0.77. So quite close, not exactly the same, but quite close. And the trends, you will see the trends in the next slide. In terms of width, it's really dependent on the spot size, and we will see more of that later on. For the thermal modeling, when we look at the med pool models, we are looking at a very localized model. So looking at the med pool and the specifics of the details of that region. But when we look at the thermal model, we are interested in capturing the thermal history of larger deposits, even the complete part if needed. So in this case, the power, spot size, scan speed, scan path are very important in addition to material properties. We basically solve the conduction equation, which includes a source term for the laser source, as well as sink terms for convection and radiation. What we get is the thermal history as a function of the deposition strategy. In this case, we see a diagram showing at a certain point 3 peaks. One peak, the first one, is as the laser approaches the point of interest, we see a small peak. It did not achieve any melting. Then the second peak is when the laser crosses that point, we have significant melting. And then we have a quick cooling with a cooling rate, which is quite high. And then we have a third peak, which does not remelt the material. That's as the laser comes in the vicinity, but it's moving away from that point of interest. With this cooling rate, we can then run thermodynamic calculations, as David showed in this presentation, to verify the properties locally and globally in the model. So the material property predictions for as-built material can be corrected if needed, if these cooling rates are significantly different. The next slide, please. We have done quite a series of simulations for Haynes 230. Here we a data was measured at CEIT for different DOE cases. And as you see, we capture the trends very well. There are small differences. It could be experimental noise, numerical inaccuracies, maybe discrepancies in properties. But in general, it's a very reliable prediction with a very good capture of this analysis.
Sorry, Mustafa, we are just losing a little bit your voice.
Okay.
Yes, a little bit.
Perhaps
you can disconnect the camera and perhaps it would improve a little bit, please.
Yes, I will do that. So stop video. Is this any better? Is it better?
Yes, I hear you better.
Okay, sorry about that. So we extended the analysis to look at what impurities would do to a Haynes 230 deposition. So at QUESTEK, the different thermodynamic calculations were performed, assuming different levels of impurities, and the properties were provided. We ran this thermal simulation and did a crack susceptibility assessment. The higher the CSC value, the higher the risk of cracking. What we see is that when we have no impurities, we have the lowest crack susceptibility. And as we add more impurities to the system, the risk of cracking increases significantly. This is now under further scrutiny to make sure that we achieve a robust build, avoiding impurities or even allowing for more impurities, but adapting the process parameters. The next slide, please. So in total, we have a process chain, very much like ICME, where one model is focused on a certain length and time scale, providing certain information, which we adopt in the next model, focusing on yet a different aspect of the process. We have talked in detail about feedstock delivery, melt pools, thermodynamic calculations, crack susceptibility. I did not present any work done yet about distortion and residual stresses, so I captured an example of repairing a steam turbine blade, looking at deposition strategies, taking the properties predicted and determining what kind of stresses and distortions are to be expected. On the next slide, we have a summary. And conclusions. Sergio, would you like to, or shall I continue? So in the LMD technology, Sergio presented the LMD technology main parameters involved in experimental DOEs, and the experimental data made for simulation validation was presented. I presented models looking at the different scales and physical aspects of the process in an integrated computational material engineering platform. We don't have to use the models in the exact same sequence I presented. The starting point really depends on what is the previous experience and the goals pursued when simulating a certain aspect. So you can start directly with distortion. The last thing I showed, that could be the starting point if needed. Within Hipermat, we continue to study Haynes 230 as a starting point but we will be continuing.
There is one question from Leire Vadillo from Stamp that was asking if which software, SE software, is used for the simulation.
We have a CFD code called CFD ACE, which was extended for additive manufacturing. Those tools are being used for these simulations. So it's ESI solution called additive manufacturing.
Okay, so it has no specific name, I understand.
We just call it ESI additive manufacturing.
Okay, ESI additive manufacturing. Perfect. So, if is any other question related to that? Okay. If not, I would say that I would have to say thank you very much to all the panelists, to the people that have been attending this meeting. Nice to have you on board. And I expect that in future we will have more and more clear results from this project or for other projects that we are developing. And we could be able to repeat one webinar like this. I expect that at some point we could do it face-to-face workshop. But at this time, I think the webinars are more easily and more safe to be made. So thank you very much to everybody. And let's see you in other opportunities, in other webinars that will be all in the future. Thank you and bye-bye.
Thank you. Have a good day.
Thank you. Bye-bye.